Hello everyone, this is lecture 79 of Principles of Electric Circuits. Let's discuss the applications of the mutual inductance. We will introduce two applications, that is the field of energy processing and signal processing. First, the central tapped transformer is applied in the field of energy processing. You see, the circuit on the right side is a transformer with a central tap. About the transformer, we will introduce in detail in lecture 81. Here, we can understand it as three coils with mutual inductance to each other. We marked the dot convention between them. We assume that this is coil 1, this is coil 2, and this is coil 3. For coil 1, the current lags the voltage 90 degrees, while for coil 2 and 3, the voltage leads the current 90 degrees. So US, U1, and U2 are in phase. Based on this discussion and combined with the dot convention, we can check the waveform of the load voltage from time domain. We assume that the power supply is a sine with zero initial phase angle. In the half cycle, when the power supply voltage is positive, according to the dot convention, the voltage of positive above and negative below will be produced on the U1 side. So D1 is conducted. And the current is like this. U2 also has a voltage of positive above and negative below. If the current would be in this direction, but D2 cannot flow reverse current, so D2 is opened, and the current cannot flow through it. We assume that D1 is the ideal diode. Then the load will obtain the voltage the same as the power supply. It's like this. Next, we look at the half cycle when the power supply voltage is negative. There will be the inductive voltage on U1 and U2 at this time. If U1 can be circulated, it must be in this direction. Due to the one-way conductivity of D1 is unfeasible. Next, for voltage U2 of negative above and positive below, the possible direction of the current is like this. D2 is closed at this time. We can find that the voltage of UR and U2 are reversed at this time. That is, the voltage of UR and US are reversed. So we can get the load voltage is like this. Similarly, do you see it? Due to the central tapped transformer, under the assist of two diodes, we get the waveform of the full wave rectification. You may compare it with the 4-diode bridge rectification circuit we discussed in the nonlinear resistive circuits. The two waveforms are the same for the load, so in practice, whether we use the central tapped transformer or use the full bridge rectifier depends on the cost, reliability, and the requirement of the load voltage. Applying the central tapped transformer for full wave rectification is a kind of practical circuit. Then let's discuss the receiver of the telephone. For a telephone receiver, it has two ports. The first is the listening port, which can be modeled as a resistor. The resistance is the model of the speaker. The second is a speaking port, which can be modeled as a serial connection of a voltage source and a resistor. Here the voltage source is the voltage of the sensor when we are speaking, and the resistance is its internal resistance of the sensor. Have you met such a phenomenon? When we are speaking using the phone, we can only hear the sound from the one we are talking to in the receiver, but cannot hear ourselves. Supposedly, the speaker and the sensor are in the same circuit, so when the sensor has a voltage, there would be generate a current in the speaker, then we can hear ourselves. So how can the phone realize such a function? You see, in the receiver of the actual telephone, in addition to the equivalent circuit of the sensor and speaker, we introduce three coils with mutual inductance. Besides, the third coil constituted an auxiliary branch. We take a look at why such a circuit can realize that we can hear another person but cannot hear ourselves in the receiver. Because the whole circuit is a linear circuit, we can use the superposition theorem to deal with the voltage of the receiver induced by speaking of other person and ourselves, respectively. We first look at the case when the other person is speaking. We assume that we don't speak at this time. The equivalent circuit is like this. The U out corresponds to the voice of another person. The R out corresponds to the equivalent resistance of a whole system looking to the right. We assume that the voltage is positive above and negative below. Then the current flowing into the coil from the left to right to left. According to the mutual inductance between the two coils, we know that inductive voltage with the direction of negative left and positive right will be got in the receiver. Similarly, on the auxiliary branch, there is also a current flow from the right to left. According to the mutual inductance, the inductive voltage of the direction is negative left and positive right. So these two voltages are superposed. So we can hear clearly. Next, we have a look at the case when I'm speaking. We suppose another person doesn't speak. So here is the equivalent circuit. We assume that the voltage source is positive above. So this is the current flow from the left to right for the coil. According to the mutual inductance between the two coils, the induced voltage with the direction of the positive left and the negative right. But the auxiliary branch, the voltage we are speaking, will produce a current flow from right to left. According to the mutual inductance, the induced voltage with the direction of negative left and positive right. So these two voltages are offset. If we can dexterously set the mutual inductance between the three coils, we can ensure when another person is speaking, we can hear the person clearly. But when I speak, the voltage doesn't have effect on the receiver. Did you find mutual inductance has very wonderful applications? Although the examples in this lecture are all three coils with inductive coupling, two inductive coupling coils also have a wide range of applications. We will introduce more in the transformer. Well, that's the end of this lecture.